Alright folks, this is Chili here, and welcome back to the beginner tutorial series. This is lesson 13. Now before we get started on today's topic, I just want to quickly go over something here. Last lesson we did tic-tac-toe and we covered a lot of new ground, so I hope you've managed to internalize all that stuff. And now what I will not be doing is I will not be showing you the solution to the last exercise, which was to create an AI routine for the tic-tac-toe game. I'm sure you can handle that on your own, but I mean, if enough people really want to see it, I guess you can ask me. If I get enough people asking on the forum, then I guess I will post a bit of a solution on there. But I mean, rather than formulating the solution, I'd just rather spend any time I have working on new lessons. So so if no one's really interested in seeing the solution to that question, then we will just move on. One thing I want to say about lesson 12 though is we learned the switch statement, which is very important, and we used the switch statement so that we could access our state variables, which are individual variables. We can access them by number by using an integer rather than by changing the name of the variable that we're accessing, right? And the reason why this is significant is because we can do stuff like this, where we can set all of the variables just using a simple loop. You couldn't do that if you didn't have this function, right? I hope that's obvious. So yeah, that's great, and it lets us use loops to do repetitive tasks. Now, think back to some of the other stuff we've done. Can you think of any other place where a loop might come in real damn handy? I hope you thought of our poo game, because I mean, look at this. Even just with our 3 poos here, we've got three sections of code here, and it's almost identical. It's just that the variable is changed. And if we had a function to access our variables there by index, we could put this all in a loop, and that would save us some space. It would be a much better solution, especially if we wanted to increase the number of poo on the screen. It's not so bad with just 3, but imagine if you had like 50. That would be a shit ton of code, and it would all be redundant. If only we could access our data by index. So what would we need to do to get a deal like that working? Well, each of our poos here has 3 variables associated with each poo object. In the other one, we only had the state variable, and that was it. So only 1 variable per object, which was a square on the tic-tac-toe grid. But here we have 3 variables per object. So if we wanted to be able to access those variables by index, we need to write a get and a set function for each of the variables. So we'd need for example, a void get poo x, right? And then we'd go int index here, and then we know void get poo y. Wow. Okay, this is stupid because it's not void, right? It's int, and bool. So this function would return an int. It's a get function, so it should return a value. Get int poo y, and I don't know. We'll get in here a bool get poo eaten. We index here. right? And we'd also have to write set functions, right? These ones would be void, right? They would be void set poo x int index and int x, I guess. I don't know. Yeah. So we'd have to do that for every, we'd have 2 functions for every variable associated with our object. So that's a lot more work, and then we'd have to put those switch statements for every one of these functions. It's a lot of work, and I mean, let's say we change the number of objects, the number of poos on the screen. Well, I mean, if you change the number of s variables, state variables here, you would have to go into your functions here, and you'd have to add new cases or remove cases. And the same thing goes for our poo. Where is it? That's not it. Can't find my goddamn. There it is. The same thing would go for our poo, except that we'd have to change a lot of more crap because we'd have like 6 functions to change. So yeah, it seems like a lot of work, and it is. But luckily, there's a better way. We can do this. We can get this functionality without going through all the hassle of making all these functions and setting up all the switch statements. We can get that, and we can get it nice and easy. But in order to do so, we're gonna have to learn a new trick, and this is a very important one. So pay attention. What we're going to be doing today is we're going to be learning how to use arrays. We're going to get arrays. I want arrays. I'm sure you guys want arrays too. So let's do it. Now before I explain to you what an array is and how to use it, I just want to go over memory again. I think I went over memory when I was talking about variables, but I forget. So, memory is like a it's like a big row or column or whatever you want to call it, a big stack of boxes. Boxes where you put numbers. All right. Data, if you will. Data is all just numbers, trust me. I'm a professional, trust me. Let me just set this up here. This is probably way more than I need, but... So, memory. You have your boxes where you store your data, and you have an address which is associated with each of those boxes. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on. All right. Now, in C++, in C, when you make a variable, when you say int, I don't know, x, right? So, speaking, I don't know, what's the word I'm looking for? Metaphorically. Not quite, but it'll go. Metaphorically speaking, when your program runs and it hits this line of your code, what happens is the computer says, okay, so you want a variable, you want an integer, x. So what we're going to do is we're going to find an open place in memory, a place that's not being used, and we're going to call that x in our head. So what we're basically saying is that in our program, x now means address 0 in memory. That's what's happening here. And then whenever you do something like x equals 5, the compiler says, okay, you wanna move the value 5 into memory address x. What was x? X was address 0. So we take 5, We stuff it in 0, and we're good to go. All right, I think I went over this before. Now, here's something new. Let's say we go int, we'll just call this list. And then we go for like this, square brackets. We type a line like this. Now when the compiler hits this line, what it says is, okay, you want an array of integers. You want an array of 4 integers. So what it does is it goes here and it says, okay, this is list. It's at address 1. And it basically gives you, I don't know what I'm going to do. Let's just undo that. I shouldn't have drawn it on the edge of the screen like this. Oh, wells. Okay, that's a bad color. I like red. No, this is the wrong one, isn't it? Let's see here. Red. Good. This one should be white. Okay. So, back to what I was saying. So it says, okay, list is at address 1, right? Because address 0 is taken up by X. It finds the next open address. But it chops off, or it carves us off four data boxes for us. So it says, all right, list, we're going to allocate these 4 addresses to list. So this thing here is all list. All right. And yeah, we can use these memory locations to store data in. I'm going to back up for a second here, just because I don't want to confuse people. I'm going to back this mother up. Back up. Keep going. Keep going. There. All right. So let's come at this again. Let me get my color out. We'll get my black on. There. All right. So again, we'll make an integer array. We'll call it list again, because I'm original like that. And so again, compiler will give us, this time all our data space is empty, so it'll give us the first location here. So this is list, and if I go down here, give me some red. Now this one's 5 memory spaces, so we'll get 1, 2, 3, 4, 5, from 0 to 4. And we'll do that. All right, so this is all list. Okay. Now here's where it gets interesting. Now say we want to store something in our list. We can store 5 integers. So we want to store something in the first location. So we go list 0. 0 is the first location in any array. Remember that. It does not start from 1, it starts from 0. So list at 0 is equal to, I don't know, 10. And so what the compiler says when it hits this is it goes, okay, so you want to store something in the array list. List starts at 0. And you want to store something in the 0th element. So we add 0 to 0, we get 0. And then we stick our 10 right in there. All right. And now let's say you want to go list 3 is equal to 9. So take a second, think what's going to happen here. Have you got it? All right. Again, compiler looks at list. It says, okay, list starts at 0. And we want to store something in the third element of the list. Notice how I paused there for a second when I said third, because what third means is we're going to add 3 to the base location. So the base location is here. We add 1, 2, 3, and we go to address 3. So in a sense, it's the third address, but it's actually the 4th thing in the list. It's confusing because everything starts at 0. Notice how when I was making my loops, I often started my loops off at 0. Sometimes I started at 1, but usually I start at 0. And the reason is because loops and arrays, they go together. And your arrays start at 0, so your loops gotta have to start at 0. It's just the way it works. All right. And likewise, if I wanted to, if I had a variable, say I make a variable int foo, okay, then the compiler is going to say, okay, well, we'll give you the next empty space here, which is 5, and that's your foo. And then what I'm going to do is I'm going to say foo is equal to list 3. So what it says is, it says, okay, list, where does list start off at? It starts off at 0, and we want the 3 element, so we add 3, so that's a 9. All right, so we got our 3 element here. It's a 9, and then we want to store that in foo. So it says, where's foo? Well, foo is at 5, so then it takes that 9 and it crams it in foo, which is at 5. And that's how that works. All right. So let's do one more quick example here. Continuing on from this, this continues on to here. Now we're gonna say, all right, I want an integer. No, we're gonna mix it up a little bit. I want a float array, and we'll call this float array. We'll call it array, and we're gonna put 3 of those in there. All right, and then we're gonna say. All right, so when this happens, right, I'm getting ahead of myself now. Compiler hits this line and it says, okay, so we want an array of floats. So, wait. So we're gonna allocate these 3 addresses to our array, which is called array. I know, it's poetry. And then we're going to want to move something in our array. So let's say we say array at 0 is equal to, I don't know, it's equal to foo. All right. The compiler says, okay, foo, what was that? Foo was 5. We look in 5, we see we got a 9. We pull that 9 out. Here's our 9. And then we say, okay, we got to store that 9 at array. Array is at 6. And we're at index 0. So 6 plus 0 is 6. And we take that 9 and we shove it in here. Fair enough? And last but not least, let's say array at 2, which is the last element of the array, because there's 3 elements. 0, 1, 2 is the last element. Is equal to, I don't know, list at 0. Okay? So again, list is 0. 0 plus 0 is 0. Address 0 is 10. We pull that 10 out. Then we store the 10 at array. Array is 6. We want to store it at index 2. 6 plus 2 is 8. We take that 10. We jam it in here. All right. So this is more or less what is happening when you use an array. So to recap, when you are declaring an array, I want to delete this crap. This eraser is too small. Damn you. I'm too lazy to change the size of this brush. Okay, that's enough. I'm done. So, when you're declaring an array, just like when you're declaring a variable, you state the type, and then you state the name of your array, but then you use square brackets and you state the size of the array, how many elements it's going to have. So you put your size in here. We'll say it's 5, and then semicolon. That's how you declare an array. And how you access elements of the array, well, again, name of the array, and then the index of the element you want to access. And then just you treat it like a normal variable. So you can shove stuff in there. You can pull stuff out. Oh, one more thing. I kind of messed up here. When you're moving, say, from foo into array 0, it's going to pull out that 9, and then it's going to convert it. It's going to convert it to a float, and then it's going to store it in here. So you're actually getting floating point numbers in here. I fucked that up kind of. Oh well, small detail, but yeah. So first it will retrieve the value from foo, then it will convert it to a floating point, then it will store it in the array. Here it retrieves the value from list 0, then it would convert that 10 to 10 floating, and then it would store it in our array. Okay, just want to clarify that point. All right, so that's arrays for you. Now let's get on it already. I've been talking about this shit for long enough. Let's do it. Do it. So, first things first. We're not going to need all these variables here. We're just going to need our poox, our pooy, and our poo is eaten. We'll get rid of these numbers here. And we'll declare them as arrays. Copy that. Get our square brackets on. Face is just a single thing. It's on its own. It doesn't need arrays for anything, right? I hope that's self-evident. Now, we got to find all the places where shit's happening that's being done on our poo. And here's one of those places. So here we have initialization of our poo variables. We're going to do this in a loop. Now, because it's in a loop, we can't just specify like specific values for our coordinates. Like if you see this, here we're putting our poo at specific places here. We can't do that in a loop, right? So what we're going to do, we have two choices. We can either use some kind of an algorithm to determine their position, for example, lining them up in a line, or we could use random numbers and we could randomize their starting position, which is actually a better idea when you think about it. You don't want your poo starting at the same place every time. It'd be not much swanker if we could get it starting at different places. So we need our stdlib, and we need our time. Yes. All right. Now, I mean, if you're paying attention in lesson 12, you know the drill here. We are going to srand, and we're going to do an unsigned int typecast here, and we want time null. There. All right. So we seed our random number generator. Now, for int index is equal to 0 as long as index is less than 3, index plus plus. We're looping through our poo, and we want poo x at index. Now we want to find we want to get a random position for the x of our poo. How are we going to do that? Well, let's get back to my drawing board here. I fucked it up, kind of. Okay, it's good. It's okay, it's okay. Say goodbye to the notes. Alright, so we've got our screen 600 by 800 by 600, and we've got our poo, right? Here's the XY coordinate of our poo. It's top left hand corner. So our poo should be able to range from here 0 0 to here some value. So we need to know the width and the height of our poo, which I forget. What is it again? Let's look at where can we find the X and Y height, width of our poo? Here. Poo is 24 by 24. Apparently. Looking at this, it seems like that's the case. So what we're going to do is we're going to go from, we're going to get a random number. Where's our modulus? And it's going to be from 0 to 800 minus 24. I'm not sure the order of operations here, so I'm going to put brackets around that, just to be safe. And poo y, this one, index, this one, there we go, it's equal to, again, rand modulus 600 minus 24. Alright, so that'll give us a random position on our screen without having our poo going off the screen and crashing our program. And we want the poo is eaten. No, I don't want a space there. You could put a space there, but I don't want one. It's not my style. Is equal to false. So we want the poo to start off in the uneaten state. And there you have it. So now we've just randomized the positions of our poo. And that's that. Now it's time to loopify the other stuff here. So we don't need loops for our drawing stuff. And this is all for the face, so that's fine. It says move cursor. That's stupid. There is no cursor. We'll say it's move poo. Not that it matters, because it doesn't. But there you have it. Alright, so here we have a statement that's hardwired to check if poo 1 is eaten, if all of the poos are eaten, basically. So if not all of the poos are eaten, then we do stuff. Otherwise, we draw a game over. Alright. That's fine, except it won't work for our arrays. I mean, we could put our arrays in here. We could, for example, could do this. And like that. And that's fine. But that would give us another problem if we wanted to change the number of poos. Then we'd have to add more statements into here. It would be a pain in the ass. That's not the right way to do it. So first we're going to have a loop to check if all the poo is not yet eaten. So for int index equal to 0, as long as index is less than 3, index plus plus. Alright. What's the deal? Okay. We're going to create a Boolean variable because we have to, the result is going to have to live outside of this loop. So we have to create a variable outside of the loop, and we will call it all poo is eaten. And we'll say it's true. So it starts off in the default assuming that all the poo is eaten. And for every poo, is equal to all poo is eaten. Which one do I want here? And poo is eaten at index. So what we're doing is for every all poo is eaten starts off as true, and for every single poo we're going to AND it with poo is eaten and store that result in all poo is eaten. So if we do that, if every poo is eaten, every time we loop through this we'll get true and true, so it'll remain true. But if even one of the poos have been eaten, we'll get a true and false. The result will be false, so all poos eaten will become false, and then afterwards, no matter what the variable or the values of the other poos eaten, this one will still be false, so the result will remain false. So it'll only take one false boolean here in our poo object to cause this to turn false, and once it turns false it can never turn back to true, right? Because this is an AND, so they both have to be true. So that's how that works. And after this loop, all poo is eaten will be it'll represent whether or not all the poo has been eaten. So we'll just put that here. If all poo is eaten, wait, if not all poo is eaten. And now we have these three statements, and they're all identical except this one is poo 1, this one's poo 2, and this one is poo 3. So what we can do is we'll get rid of these ones and we'll loop her up. So for int index is equal to 0 as long as index is less than 3, index plus plus. Alright, now we convert this. So get rid of that. And index. There we go. We've converted it to our array system. Copy that. This one's poo1x, poo1y, poo1x, y, eaten. And now we just delete these numbers here. There you go. Good night. Good riddance. And I think, no, that is not everything. Ah! There. Got ones here and here. You tried to sneak that one by me, didn't you? Alright, so now we have everything accessing by index, and it should be okay. And that, my friends, is that. We have just converted our program over to using arrays. I think. I could be missing something here. Let me think here. Nope, I think that's fine. Let's build it. Let's see if I have screwed something up horribly. I probably have. Oh my god, it actually worked the first time. That is ominous. Yeah, I know I'm a bit of a pessimist, but just freaks me out whenever things work right the first time. Means that there's like usually means there's some kind of a insidious bug hiding behind the scenes. But apparently that has worked just fine. Yeah. So, congratulations to me. Now, here's the magic part. If I want to change the number of poo, I only have to change a few numbers and it'll be all kosher. Let's say I want 10 poo. Now with the old system that would require a lot of cutting and pasting and a bunch of just farting around. It would piss me off. But look at this. All I got to do is change basically all of these loop numbers here. So I got change 1 here. And I got to change this one. Change that one. And what else? Change that one. That one. And that one. And I think that's it. And now I should have 10 poos. It's that simple. Unless I missed one, and then we're screwed. Nope, looks good. Looks like I got my poo. I got my poo on. Yeah. Good times, good times. Now there is room for improvement here. For example, if every time I had to change the number of poos, if I had to go and find all of these 10s here, or whatever they are, all these numbers in the loops, and change them, that would be a pain in the ass. Now one thing you could think of is like, okay, well, I know how to solve that. I'll just make a variable here. I'll make a variable int npoo, and then I'll say something like this. This is npoo, and this is npoo, and this is npoo. Whoa! Almost knocked something over there. Also, I think someone's house is burning down, but I'm pretty sure it's not mine, so that's good. And then yeah, we'll go here and we'll say we'll say npoo here. We'll initialize it. We'll say npoo is we'll say it's 10. No, we'll say it's 15. I'm gonna get a little risque. Copy that, paste it there, and there, and there. Alright, so now we've variabilized it, and we initialized the variable here, so it stands to reason that we change this number, one number here, and everything will change then. So let's try that out. Spoiler, it will not work. Whoa, look at all those errors. npoo is not a type name, static, or a numerator. npoo is undeclared identifier. That's not cool. It's right here. I just declared it. Now you're saying it's not declared? Well, there's a number of problems with this. The problem the first is you stay there. Okay. Problem the first is, how do I say this? When you specify the size of an array, you can't use a variable to specify that. All right, it has to be what's called a literal, or like an actual number, like 3 or something, right? And the reason for that is the compiler has to know at compile time how big that thing is going to be, because it needs to know how much space it's going to have to allocate. So you can't go ahead and make it a variable, because variables can change and the compiler won't be able to handle that. So, long story short, you can't use a normal variable in here. That's problem number 1. And I don't know, there might be other problems, but that's the only one that really counts here. So, we're no-go on using a variable in here. Now, using a variable here, that's perfectly fine. There's no problem with that. And so we're going to leave that. But what are we going to do for this one? Well, we could hard code it again. We could say this is 15. This is 15. This is 15. And then we just have to change this one, this one, this one, and this one. So that reduces the amount of shit we have to remember to change. And it works. But we can do better. We can do better than this. Have a little self-respect, a little dignity. We know we can do better than this. And to do that, we're going to use something called a define. Now, define is a way of making a constant. Remember I showed you constants before? That was one kind of constant. This is a little bit of a different kind of constant. We're going to call this npoo, all caps. I'm going to say it's 15. And so we're defining this symbol here, npoo, in all capital letters, as 15. We'll put npoo here, npoo here, npoo here, and npoo here. Alright? And what that means is, let me just compile that. What this is saying here, I don't think I've gone over this before, but these statements with the pound sign in front of them, like include and define, they're called preprocessor directives. And there's something that that gets processed before the compiler even sees your code. So for example, the include preprocessor directive, what it does is it finds this file d3dgraphics.h, and it just takes that whole file contents and it just pastes it right in here. So it actually includes that whole file right where you put the include statement. So what the compiler sees is the compiler sees, it sees this code here, of course, but before it sees that code, it also sees the whole contents of direct d3dgraphics.h and the whole contents of keyboard.h pasted right in here. So the compiler actually sees a long string of stuff, just a whole concatenation of H files. Not important. Here, the define statement, what that does is the preprocessor says, okay, so npoo is actually 15. Npoo is defined as 15. And so after it sees this define statement, anytime it sees npoo, it deletes the npoo and replaces it with this 15 number. So this is actually as if 15 were written here. And the advantage to using this over just writing 15 is that now if we change this one number here, it will change all the places where we have npoo. So we can change the number of poo on the screen by changing one number. Now we've created a giant lever. Just one small change here will change the entire program. And this is the best we can do. So yeah, I mean, if I put this as 2, and then I push the wrong button because I'm a derp, and then I push the wrong button again, and then I undo, and then I compile and run. There we go. We've got 2 poo on the screen, and it's game over. And likewise, if I were to put it at 22, and now we've got 22 poos on the screen, all at the basically at the touch of a button. And that is a hell of a lot better than the case when we just had, you know, individual variables and we had to like copy and paste and change a whole bunch of crap. Way hard, and this is way easy. This is the way we're going to do it. Now I could also just get rid of this int poo here and replace all of these npoos with the capital npoo, but I'm not going to, because this will be useful later. It'll be useful to have our the actual npoo that's used in our loops. It'll be useful to have that as a variable, and you'll see why later. Alright, so we have arrayified the poo eating program. And now I would like to do a little bit of house cleaning here. This is something that I probably should have introduced at least in the tic-tac-toe game, but I forgot about it. So we're going to do it now. I talked about this a little bit before, but in general, when we're going to be making real sort of programs and stuff like that, not just simple tests, we want to follow something called the model view control, I don't know, architecture, I don't know what you call that, pattern. So basically, model view control seeks to divide our program up into 3 rough sections. Now the model section is the part that it stores the state of the, well, in our case, the game, the state of the game, and it's the part where you do all the processing involved with the logic of the game. All right. And that processing it depends on 2 things. It depends on the state of the game, and it also depends on input. So control is input. In our case, it's going to be keyboard, right? It can be other things in more complicated programs, but for us, it's just the keyboard. And that's basically all that control is for now. And so the model takes the input and it combines that with the previous state, and it comes up with the next state, and it holds the states. And then view takes the state information and it presents it to the user in some way. In our case, it's going to be on the screen with put pixel calls. So we want to partition our program into these 3 sections. Now we have separate routines for keyboards and stuff like that. So control is pretty well separated out from the rest of the program. But here's the problem. With the way our program is right now, first of all of the drawing code and the state updating code is all locked up in the same loop here, and that's not good. That's not actually a good thing to have. So we're going to fix that. We're going to separate out the drawing from the updating, and we're also going to do something that I should have done before. See, up until now, we've basically done all of our logic inside of the compose frame function. But really, this function should only be for drawing. That's the whole thing. Compose frame. It's composing a graphic frame to be presented to the screen. So up until now, I've been using compose frame to put all of the main logic of the program. But really, that should be going in the game go function. That's what I originally intended it to be. My original intent was you have go, and what go does is it calls the logic, and then it calls the drawing. So drawing, of course, being the view stuff, and logic being the model stuff. But yeah, I never really got around to that. I sort of forgot about that. So we're gonna fix that short sight right now. Short sight. That's not even a word, is it? Oh, whatever. So let's divide things up a little bit here. We'll make some functions. We'll call this one void update face and void update poo. So these will be our logic functions for updating the player sprite and updating the poos. So we'll put them in here. And this is simple. We'll just be copying and pasting from the code that we've already developed. So face, right? That's basically all this stuff up until here. So just cut that. And I'll put it in here. It's good to break this shit up, put it up in its own functions and stuff. Add a little structure to the program. And the update poo is basically this stuff here. Now, we'll leave it as it is like this. Now here's the problem. We got the poo in this loop here. It's nice because we're already looping through all the poos, so why not draw it while we're looping through and updating them? So, I mean, it's nice, but it's not good to link the drawing and the updating together so tightly. So we're going to have to factor that out there. And here's what we're going to do. We'll get rid of that. Draw game over 375, 275. Got to remember those numbers. Okay. So compose frame is where we're going to be doing our frame drawing. So we'll go for int index is equal to 0 as long as index is less than npoo index plus plus. We'll draw our poo. Now one thing we've got to do here is we've got to say, okay, if poo is eaten, we don't want to draw every poo, we just want to draw the poos that have not been eaten yet. So we're going to put an extra O there. If not poo is eaten. And then we draw it. Alright. Now, I'm not sure if I like the way this is handled here. I mean, we might as well loop through everyone. There's no point in skipping this loop if they're all eaten. See, originally this was basically an either-or situation. So if they were not all eaten, we would just update and draw. But if they were all eaten, then we do the draw the end screen. But since we're separating the drawing and the updating out, this becomes pointless. So we're going to remove this test here. And now what I'm going to do I'm going to make all poos eaten. I'm going to make it a member variable of our game. So it's going to persist. And we're going to test for it after we've updated all the poos. Makes sense to test after we've updated because during an update one of them might have been eaten. So this will eliminate a one frame lag in the removal of the poo, but all in all it's not a big deal. whether it becomes before or after. Alright. So now every time we update the poo, it updates the eaten state of every poo, and then it also updates the global state of all poo eaten or not. And yeah, face, that just updates our face. That's not a big deal. So now we just got to put it all together. Compose frame just draws all the poos if they're not eaten, and then it draws the face. And now we do our go. There's one more thing we got to draw. We draw all the poos. We draw our face, and then if all poo is eaten, draw end screen. Damn it. Draw game over, that's what it was. I think that was 375, 275, 275. Alright. So we made that all poos eaten the member function, or member variable, so now we can also use it inside of the compose frame function. So update poo updates the all poos eaten variable, and then compose frame chooses whether or not to draw the game over screen depending on whether all poo has been eaten or not. We'll put the face last. That way the face can be drawn over top of the game over screen, like it was before. So here we have, let's put spaces between here. Here we have just our drawing code here. And then here we have only our update code. So it's been split apart. And I think it's definitely a change for the better. Now we have to, in our master main routine or main function here, we got to call our updating code. So we go, we'll do update face first. Update face, update poo. So we update, which is our this is our model functions here to process the simulation. Then we begin drawing, compose the frame, end drawing. Now the program shouldn't change at all, but well, unless I've screwed something up here. Okay, what's the problem? Alright, I know the problem. It's the same thing we do every night. Try to take over the world. And then fail because we forgot to put our scope. We forgot to scope our functions. And now we succeed. So let's just make sure it works. And it seems to be working fine. I see no problem with this. Gentlemen, do you? And I'm just gonna make sure I get all the poo. Oh, this game is so engrossing. I could put this on Xbox Live, man. Make myself a fortune. Alright. So that's that. We didn't actually add any new features to the program or anything. We just cleaned it up a little bit. We rearranged the junk in the trunk, so to say. And this will become useful. This will help you in the homework assignment. Right, but the main thing that I want to do, or to get across here, is that from now on, we're going to be doing a lot of, we're going to be changing this go function here. So this is the main place where everything happens. And then this function will dispatch to lower order functions, such as some logic functions, updating functions, and drawing functions. Compose frame, which is the main drawing function, which then calls subordinate drawing functions such as draw poo, draw game over, draw face. Fair enough. Now, we did, since we've implemented arrays, it's given us the power to, with a single keystroke, change the scale of our program from just a few turds on screen to a multitude of turds. Now let's say that this power it could go to someone's head, right? They could go a little drunk with the power, and they might say, "Okay, I'm gonna get 100 poos." That's a lot of poo. That is a lot of feces. How would that work? Well, it would work. You'd imagine it would work about the same, except, yeah. Do you notice something here? Notice how the Mr. Face guy, he just doesn't seem to have the energy that he had before. Something's wrong with him. Seems a little sluggish. Might have had a rough night or something, but I don't know. Let's just try to eat some of this poo at this snail's pace here. Still moving rather slow. Is it just me, or does he seem to be getting a little bit faster? Seems to be getting a little more spry. Maybe the poo is giving him energy or something. Although I doubt that's the case, especially looking... Whoa, he just kicked it into overdrive here. Looking at the expression on his face, it doesn't seem like he's enjoying it very much. So what's the explanation? Well, obviously, when we have a few poo on the screen, he moves pretty fast. But as the amount of poo being drawn on the screen increases, we are getting less and less frames per second. So of course our face is moving more slowly, since the speed of his movement is tied directly to the frames. So that is a problem. Now basically there's two places where you can put the blame. Either the hardware simply can't handle drawing that many things on the screen at once, or there's a problem in the algorithm. Now, I mean, 100 poo faces. Let's get out our calculator here. All right. So we got 100 poo faces right now. The poo face is... It's actually 24 by 24, although we don't... Some of those pixels are transparent, so we're not going to draw them all. But let's imagine that we're drawing every pixel. That's 24 times 24. 576 pixels per poo face. Right, times 100. So that's 57,000 pixels being drawn for the poo at 100 poo. Now, I don't know if you know a lot about current graphics hardware, but filling 57,000 pixels is nothing. That is absolutely nothing for current hardware. I don't have a bad video card myself, so that should not be a problem. And yet, we're getting some serious slowdown. You may have seen the slowdown before in some of my earlier assignments. For example, the one where you have to draw the rectangle. The resizable rectangle, the filled-in rectangle. And you might have noticed that if you make the rectangle rather large, the frames, they just drop right the hell off. And yeah. So the reason is because there is there's a bit of a flaw in the D3D graphics put pixel function here. It's not so much as a flaw, but it's definitely inefficient the way it is right now. There's a reason why I made it like that, but I didn't have to, actually, now that I think about it. And at any rate, we can't continue on like this, because when we're going to make a game, we're going to want a lot of shit on the screen. And in order to do that, we're going to have to kick things up a notch. So, the next thing we're going to be doing in this lesson, yeah, I know it's long, but, you know, you can take a break whenever you want. You don't have to do it all in one sitting. Next thing we're going to do is we are going to speed up put pixel by like a factor of 100. I've never measured it, but I think it's a really huge speed up. We're going to have to do some open heart surgery on the guts of the framework. So this is your first sort of sneak peek into the framework. I'm not going to explain the whole damn thing, but I'm going to have to explain a little bit about hardware and shit for you guys to understand what we're doing. I don't have to explain it. I could just show you what to do and you just do it, but it's a good opportunity to get a little bit on this in. We're not finished learning about C, but we can sneak a little bit of this framework stuff into here. So, a little bit of the DirectX API. So the first thing I'm going to have to do is I'm going to explain some stuff about memory. It's good, we just learned about arrays, so... damn it, I didn't want to push that button. I wanted to put this button, and this one. And then this one. Alright, so, memory. You've got something called a CPU, right? That's the thing that runs the program. It does all the stuff. It's the foreman of our PC assembly line here. If we think of our PC as a big factory or something, the CPU is the foreman. He also does the most of the work too, so he's not your typical foreman. But whatever. You got a CPU and you've got RAM, right? They're connected by a big fat bus here. It's not a school bus, it's a bus where information travels. Now the RAM is where the program is stored, all the code, the instructions for the program, and where all the data is stored. Your variables, your arrays of shit. But let me think here. So you've got your RAM, right, with your addresses. This is your address numbers here. So you start off with address 0000, blah, 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 blah. There's a lot of, boxes to put stuff in memory, like billions. So I'm not going to write them all out, but let's say that you've got, from 0000 to 9999. I'm not going to write in hexadecimal, but you get the idea. And this is your RAM. This is where all your variables and shit goes. But that's not the only thing that is in memory. In memory space, your CPU is hooked up to your RAM, but it's also hooked up to your graphics. And it's also hooked up to, example, your sound and your Ethernet, etc. And it just so happens that a lot of the input and output to these devices also goes through memory access. So, for example, memory addresses 0 through 9999 might be mapped to the RAM. So when you put something, when your CPU moves something into address 0000, it goes into the RAM. But address, 10,000 to, let's say, 20,000, this might be mapped to your graphics. And address blah blah to blah blah might be to your sound, and the next one might be to your Ethernet. This is called memory mapped I/O. I/O standing for input and output. And so what it means is that, when you want to communicate with your graphics card, you just have to send data out to a specific address in memory. And there's a little device here or somewhere called a memory mapper. That might be what it's called. I forget. That's what I'm going to call it, a memory mapper. And it will determine if it's, okay, so it's address 00, or let's say it's address 1000. Well, that's going to go to the RAM, so it'll send that to the RAM. But if it's address, 10,000, it'll say, no, that's going to the graphics card. So, moral of the story is that memory doesn't just mean storage in RAM. It can also mean access to peripheral devices. Now, why am I telling you this? I'm not exactly sure, but I think it'll come in handy. So I'm deleting this now because it's taking up too much space. So, here's the deal. Let me tell you a little bit something about graphics. When you got graphics, you've got a screen, right? And that screen is composed of pixels arranged in rows and columns. Okay, beautiful. And it just so happens that those rows and columns of pixels are represented, or they're stored, in memory. So each one has an address here, right? Memory, you have your address and your data, right? And so address 0000 here might correspond to pixel 00 here. And address 0001 would correspond to pixel 10, and so on and so on and so on. And if you change the value of one of these locations in memory, that will change what color is displayed in the corresponding pixels on the screen. And that's what we've been doing here. We've been basically just changing pixels in memory, the values in memory that correspond to the pixels in our window. That's what we've been doing. That's the whole thing that putPixel does. I mean, that is how graphics used to work. Like, again, you have your CPU and you have RAM. That's supposed to say RAM. And then you have your graphics card. And your graphics card has VRAM. Yeah, VRAM. And that's also hooked up to the bus. And so when your CPU when it puts data to certain addresses, that data gets transferred and it goes into the graphics card's VRAM. And then the graphics card had something called a RAM DAC, which is a RAM digital to analog converter. And what it would do is it would read the locations in memory one after another, and it would shoot out signals. And those signals, which are like squiggly lines, would go to your computer monitor. And it would control the the electron beam that would create the lines on your monitor. And that is the magic of graphics. So basically, graphics is just a big array. It's an array of pixels in memory. Now you might be saying to yourself, wait a minute. Arrays are just like one-dimensional lines of boxes, right? But the screen is like a two-dimensional grid of pixels. So how does that work? Well, if you remember from our tic-tac-toe game, we had a kind of a one-dimensional way of accessing our pixels, or not our pixels, our our square state variables. So they were going from 0 to 8, right? And what we did was we created a function that would map x and y values to a one-dimensional index value. And that's all that's happening here. So imagine that you have... That's not good. Let's try this again. Imagine you have your monitor, and you have a pretty shitty monitor. The resolution is 4 pixels wide by 3 pixels tall. Your good old-fashioned 4:3 resolution, or aspect ratio. So, as a one-dimensional array, this would have, you have 12 pixels, so you'd have 12 elements, right? 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. There we go. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Perfect. And so pixel 1, this is pixel 1, right? This is pixel 0. I said it wrong. I screwed that up. This is pixel 0. 1, 2, 3, and then 4, 5, 6, 7, 8, 9, 10, 11. And that is the correspondence relationship between the pixels on the screen and the video RAM. This is your VRAM. Alright? So if we wanted to change the pixel, this pixel here, we just move some data into VRAM location 5. So if we had an array, and that array was called VRAM, we just go VRAM 5 is equal to whatever color we wanted. And that would fill that color into this pixel. And that is how we draw on the screen. Alright. I hope I've explained that fairly concisely. So what is the problem here? I mean, why is this going so slow? What's the big holdup? Back in the day, this was how you did drawing. You had your CPU, and it was connected over your PCI bus to your graphics, which had your VRAM. That's VRAM. This graphics card is too small. I'm gonna make it bigger. It's gonna be this big. And your bus is connected to your VRAM, which is also connected to your RAM DAC, which is connected to your monitor. Alright. And yeah, basically you would just do what we're doing right now. You would just do put pixel calls. Just alter the memory locations that correspond to the VRAM. Put numbers in those locations, and that will control what is being displayed on the screen. But as computers got more sophisticated and stuff like that, and games and stuff, they demanded more graphics. What you ended up having was a GPU, kind of graphics processing unit, which does a lot of... Wait, I'm going to change this. Does a lot of the graphics work for you. So instead of having the CPU directly accessing the VRAM, which is slow because that has to go over, you know, your PCI bus or whatever bus you're using, AGP bus or whatever. And that's like, the bus between the RAM and the CPU is a nice big fat bus. But the bus between the CPU and the video card is it's pretty skinny compared to that between the RAM and the CPU. So it's slower. It's slower to have the CPU accessing the VRAM. What you want is you want a GPU, a graphics processing unit that's right on the graphics card, that has a nice big fat bus to the VRAM. And you want the GPU to be doing a lot of your work for you. Like, for example, sprite drawing, and definitely in like 3D rendering applications. You want your GPU to be doing a lot of that work for you, because it's just a lot closer to the VRAM than the CPU is. And if you have your GPU doing that work, your CPU can be doing other shit while that's happening, and then you've got your parallel processing going on there. So, as the hardware evolved, now you have your GPU accessing the VRAM. But what happens if your CPU also wants to do some direct access on the VRAM? Now you have a problem. They're going to like bump heads and shit. Because they're both going to be trying to grab at the VRAM, and they're going to bump into each other, and they're going to blow shit up. And that's not good. So what you have is you have a mechanism. You need a mechanism to say, okay, I call dibs on the VRAM. The GPU will actually lock the VRAM. It'll put a lock on that mother. It'll say, okay, this is locked right now. You can't touch it. And the GPU will maintain that lock until it's finished with the VRAM. Then it will remove the lock. And once the lock is removed, then the CPU can say, okay, I want to use the VRAM. And then the CPU can lock the VRAM and stuff like that. So back in the day, it was no problem. The CPU could access the RAM whenever it wanted. But these days, the CPU has to basically ask permission, because the GPU, the default state is that the GPU owns the VRAM, and the GPU has a lock on it. And if the CPU wants to directly access it, first it has to request the GPU to relinquish its control of the VRAM. Then the CPU locks the VRAM, and the CPU will maintain its lock on the VRAM until it's finished. Then it removes the lock, and then the GPU can access it again. That's to prevent them from bumping heads. You know, getting into a lightsaber fight there. So, why am I telling you this crap? Now, because you know a little bit about how graphics is working, at least in our framework, now I can explain the put pixel function to you. The put pixel function, it does two things, or three things. The first thing it does is it has to lock the back buffer. The back buffer is basically, it's just the part in VRAM that controls our screen. So our window screen memory is the back buffer. And what we want to do is we want to get access to that memory, and we want to change a number in that memory, which will change a pixel in our window. But before we can touch that, we have to beg the GPU, we have to beg DirectX to give us access. So the first thing we do is we get an interface to the back buffer. This doesn't do anything, it just gives us an object that represents the back buffer. So I'm not going to explain exactly how it works because it's pointers and I haven't taught pointers yet. But basically we get an object, we get the back buffer object here. I mean, it was always existing, we just get an interface to it. And then we use our back buffer interface to lock the back buffer, which is basically saying, okay, we want to touch the back buffer now. So please give us exclusive access to the back buffer. And we lock the back buffer. And once we've done that, what'll happen is this function will it will fill in a bunch of data into this rect object, D3D locked rect. And the D3D locked rect or rectangle object, let me just show you. It has this object or this structure, it's actually a structure, but it has two members. The first member is p bits. That is a pointer. It's basically an address in memory. It's the address in memory of our video buffer, our back buffer. Basically, it's the address in memory of our window, graphics, screen, thing, surface. Blah. And the other thing we get is the pitch. Now the pitch is just, let me go back here. Damn it. There. Let's say we have let's say we have our graphics surface here, our screen. In our program, it's 800 wide by 600 tall. And the pitch is basically just how many pixels are in a single row. It's a little more complicated than that, but for our intents and purposes, just think of it as how many pixels are in a row. So it gives us the how many pixels are in a row on the surface, and it gives us the address of the first pixel on our surface. And so once we've called lockRect, it does two things for us. First of all, it tells the GPU that it has to finish what it's doing on this surface, this back buffer. And once it's finished, it has to relinquish control, and it gives control to our program. Our program gets a lock on it, so as long as our program maintains that lock, the GPU or any other process or program cannot touch that area of memory. That's the first thing. We get a lock on it. We acquire a lock for the surface or the back buffer. The second thing is that when we acquire that lock, we also get the address where the back buffer is stored, the address of the first pixel on our screen. And that's important because we don't know where it is. The way memory works in modern computers is you can never tell where it's going to be. You can't predict that. So you have to get DirectX to tell you where the address of the first pixel will be. And it does that through the same function that you use to lock it. So once we've called lockRect, we are given permission to touch the goodies, and we are given the address of the goodies. And then we do some magic here, which I won't explain yet because it's pointers. But what you can think of it is you can think of this as kind of an array. See, look, we have square brackets here. This is an index. The index is starting from our address here, the address that we got from lockRect. And then we're using this index to choose a specific pixel within our screen here. Now this might sort of be familiar to you. If you remember from our tic-tac-toe game when we were converting from linear addressing to two-dimensional row and column addressing, we had X plus the width, which is pitch here in our case, the width times Y. So it's Y times the width plus X. And that gives us our linear address. And we just take our color, remember R, G, B, our three color values, and we pack them together into one pixel value. Basically, a pixel is just the RGB values all stuffed together. And we take that pixel value and we stuff it into the memory address of the back buffer here, our video memory. So that's all that putPixel does. It locks the memory, then it moves a pixel value into the memory address using kind of like a kind of array indexing. And then once we're finished with it, we have to unlock our surface. We have to unlock the surface and let the video card again access the surface. We cannot simply lock the surface once and then hold on to it for the duration of the program. And the reason is because we also call functions such as clear, which clears the screen, and present, which presents our back buffer to the actual monitor to be displayed. And these functions, they are things that the GPU has to do. So the GPU has to be able to access our back buffer. And it can't do that if we lock it all the time. We just maintain a permanent lock. So we have to unlock the back buffer when we're finished with it. Otherwise, we cannot clear the screen and present it to the user. And that is how putPixel works, more or less. Now the problem is it turns out that lockRect, this locking function, I'm not sure about unlocking, but definitely locking, takes a really fucking long time to work. It takes a really goddamn long time. So every time we draw a single pixel, we have to lock this. We have to lock the back buffer, and the locking, there's a huge latency or a delay. A lot of time spent just waiting for the GPU to respond, to release its control, and then to give us the address. And you have to do that for every single freaking little pixel. And that's why when you draw like 57,000 pixels, sure, moving 57,000 bits or 57,000 I don't know, integers into memory, that's simple, that's nothing. But if you have to lock and unlock the surface every single time you draw one pixel, that will slow your program down, and that is what is slowing down our program. Whew. It was a long explanation, but it had to be done. Now, you guys asked for it. You guys are always telling me about, complaining you want me to teach more about the DirectX and everything, blah, 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 blah. Well, you got it now, so I hope you liked it. We'll definitely be going over way more technical stuff once I've finished teaching the C language, which will not be too much longer. But this was just a kind of a sneak preview, because we have to fix this. If we want to move on, if we want to do more interesting things, we're going to need to draw a lot more pixels on the screen. So we're going to need a faster drawing routine. And that's what we're going to do right now. So the problem is that we don't want to lock the rectangle for every single pixel. But we still have to unlock it before we present, and we still want to have it unlocked when we're clearing. So we first, basically the order of how things are going to work is when you draw a frame, you want to clear the screen, then you want to draw, then you want to present it to the front buffer, which is what the user actually sees. There's something called the back buffer and the front buffer. I'm not going to explain it right now, but we'll get to it later. Anyways, you want to clear, draw, present. And clear and present, you have to have the buffer, I'm pretty sure you have to have the buffer unlocked for both of these. Definitely for clear, but also probably present. So you want to have it unlocked, but we want it locked for draw. So all we have to do is we can lock it once here. After we clear, we lock. And then before we present, we unlock. So that way we maintain our lock during our drawing phase. But before we draw, it's unlocked. And after we draw, it's unlocked. So it's unlocked from here to here, because it's just a loop, right? It just repeats. So it's only locked inside the drawing. We unlock it when we're finished drawing, and then when we start drawing the new frame, we lock it again, and then unlock it when we're finished. That way we're only locking and unlocking once per frame, which is about as good as it'll get. So it seems very easy. We just put the locking stuff after the clear in our begin frame. But the problem is that the locking stuff will give us our pointer to our memory, and it'll give us our pitch, right? This rect thing here. And it'll also give us our back buffer surface here. So we have to be able to remember these data, we need to remember this interface, and we need to remember this rectangle from here to here. So to do that, we'll make we'll make them members of the object instead of just simple variables inside of the function. We'll make them members of the object, so they'll persist between function calls. So we'll go to graphics.h. We're going to add these two variables. Bah. We'll add that one, and we'll add the rect. Now, just to be thorough here, we're going to initialize go to hell, you cocksucker. There we go. What was it again? I'm not even going to remember. Just going to copy and paste. Back buffer. And we'll just initialize that to null using initializer here. I won't go, it's a pointer, and pointers should always be initialized to null if you're not using them. It's just good practice. So we have p back buffer and our rect. Actually, I'm going to change this to what should I change it to? We'll call it back rect. And okay, now I got to change these ones. Back rect, and this one's back rect. I should just use a find and replace. Back rect. Back rect, back rect. Okay, so that's all of those. Now, the get back buffer and the lock, we'll call these after we've cleared the screen. There. So first we clear the screen, and then we lock our surface, our graphics memory. All right. We don't need these ones here, obviously, because these are now member variables of the graphics object. And what we want to do is, before we present the screen, we want to unlock the rectangle, and we will release the back buffer. I mean, we don't have to really release it. But, now I'm waffling here. See, this get back buffer, we could actually just do this once at the beginning of the program, and then just maintain this back buffer object, or this interface. I'm gonna do that. I don't want to confuse you guys though. What to do? I'm gonna do it. So we're not gonna initialize back buffer to null. I could, but nah, I'm not going to. So after we create device here, we're gonna go, geez, p back buffer. No, wait, that's stupid. We want to get the back buffer, so we'll get this here. So here we create our device, and then we use our device to create our back buffer interface. So in our constructor, we get our back buffer. So for getting something in our constructor, we should be deleting it in our destructor. I'm not going to explain all this to you guys. This is what we're going to be learning when we start doing C++ stuff. It's not that complicated, but just for now, just do what I do. Just do what Chili does. So here, we check to see if we have our back buffer, and if we do, we go p back buffer pointer to release, and we set it to null. Because that's good programming practice. Alright, so I hope you're following that. What we're going to do is we're going to get our back buffer. We're going to put this line after create device. We're going to add these lines after we're going to add these lines to the destructor here. And now we don't have to get back buffer every frame. It's probably not going to be much of a speed up, but I like this solution better. And we're not going to release the back buffer after every frame. So all we're doing now in our begin frame is we're clearing it, and then we're locking it. And in our end frame, we unlock it and present it. Clear, lock, unlock, present. And in between here is where all the put pixel calls are going to happen. Now put pixel, this is fine. It's just our rectangle. Alright. Actually, I'm going to do something here. And I want you guys to do it too. And that's, you cock. There. We want, what was the name of it again? Back rect dot. That sucks. Never mind. Don't put it here. Put it put it here. Back rect dot p bits is equal to null. Just set this to null. It's a pointer, so I want the pointer to default to null. It's just good practice. Alright. So I mean, before we had all of this lock rect and unlock, back buffer, get back buffer, and release. We had it all in the put pixel. And that was being called every single time we drew one pixel. But now, when we draw a pixel, all we're doing is we're just doing a simple memory move. We're moving this value here, which is just our RGB, into some part of memory, calculated with our X and our Y. Alright. And this will give us a super speed up in memory. Didn't even fail on the first try. That's pretty ominous. I'm sure it's good. I'm sure it's great. It's gravy. So we've got 100 poos on the screen right now. Let's start. And normal speed. No problem. No frames dropped. Nothing. We've got our nominal speed here. So let's try 400 poos on the screen. Still no problem with speed. We're still running at full frames per second. Alright, now remember before it was like 50 poos on screen would slow the bugger down. I've got 400 on screen right now. Let's try 4,000 poo on the screen. I don't think I started it. There we go. There's 4,000 poo on the screen for you. Oh, it's starting to slow down. Okay, so maybe 4,000 is a little bit too much for our current graphics algorithm here. It is a lot of poo. I mean, later on we'll be able to do 4,000, but we'll require a different technique for drawing. But I mean, I'm pretty sure that with our current speed we can still do quite a bit. I mean, you could make any kind of game. Like if you wanted to make like an RPG, like a square soft type RPG, you could definitely do it with this the current drawing system that we have here. Let's try 1,000 poo on screen. 1,000 is still full speed. I think 2,000 might actually slow her down. $2,000 is a little slow. Yeah, so our maximum drawing capacity is somewhere between 1 and 2,000. Maybe 1,500 or something. Seems about right. Well, less than 1,500. Maybe even like 1,700 would be enough. Let's try 1,700. Now I'm just wasting time here, but fuck it. I want to see what our limit is. Yeah, it's about 1,700. A little bit off. 1,700. That's about as much poo as we can draw on the screen at once without dropping frames. Now, mind you, I'm also running a screen capture program, which is slowing me down a little bit, but you get the idea. Basically, we have, I don't know, I think we've probably, before, I think we would start dropping frames at around 40 or 50 poo. So we've increased it by a factor of 10, about 50. So it's about 50 times faster than it was before. 5,000% increase in speed. That is not too shabby. That is nothing to bite your thumb at. All right, so we've done a little cleaning house here. We separated our program into the model view control type deal. And we've also done a little open heart surgery on our D3D graphics here and given her quite a boost, quite a kick in the nards. And now it is time for homework. You guys got to do some programming. So your homework is, let me show you what it is. I have made a game based on the code from our, see if I don't get killed. Oh, I was close. Oh, damn it, get out of the way. Oh, I wasn't fast enough. I couldn't find my, oh, God. All right, so here's the game. This time, the object is not to collect the poo. The object is to avoid the poo, which seems a little bit more realistic when you think about it. And you want to collect, well, there's got to be like a goal that you want to collect. In my case, it's these, it's these little yellow balls here. It's like Pac-Man, only with more feces. Yeah, you want to avoid those poos. Get the ball. Oh, that was a dick move. That one just appeared right where I was. That was, oh, that's a dick. Okay. Oh, God, no. I need to put my left hand on, yeah, because I can't react fast enough here. All right, get out of the way, shit. Okay, good. Right, so you want to get these things, and every one you get, oh, you cocksucker. Would you just let me explain this freaking game? Every one you get will increase the amount of poo on the screen. So the difficulty increases. It's kind of like, you know, next level kind of deal. Get away from my yellow thing. It's my lemon. All right. I'm getting quite a few of them now. Now there's quite a few poo on the screen. Now it's getting hard. All right, avoid that. Wow, shit. Okay, I lost there. But you get the idea, right? So I want you to make a game like this. Basically just make this. It doesn't have to be exactly the same, but there's a few little tricky things in this thing. tricky thing number one is, if you'll notice, the poos, they have a lot of different speeds to them. They move at very different speeds. And there's a way I've done this, a technique. It's very simple. I'm not going to tell you what it is, though. I want you to think about it. It's a little puzzle. But you can get the poo to move at basically any speed you want it to move. From like crawling across the screen very slowly to zipping across the screen super fast. And it's very simple. You just have to change the way that we've been handling the position variables. The other thing is drawing this filled in circle here. It's not a I mean, I've showed you how to draw a circle outline, a line drawing circle, but a solid circle we have not done yet. So you don't have to do a solid circle. I mean, if you cannot figure out how to do that, then yeah, you can just use a normal circle from our algorithm that we've already developed. Just copy and paste it. But it's a challenge. If you want to try to make a solid circle, you can try that too. But the basics of the game is changing it from, changing it from collecting the poo to avoiding the poo and collecting some other object. And the poo should move. I mean, if the poo's not moving, that's not very interesting, okay? And also, the amount of poo on the screen should increase. That might be difficult for you guys, but I swear to you guys, I did not use anything to make this program that I have not already taught you. It's all stuff I've shown you before. So you should be able to do this. You're just gonna have to try for a while. Just like get off your lazy asses and put in an effort, for Christ's sakes. Nah, I'm joking. No, you guys work really hard. There was this one. Oh man, I wanted to show you guys before, but I kept forgetting. But there was this one guy on the forum, and he made this crazy Pac-Man game. I'm gonna show you guys. Let me see here. He made this crazy Pac-Man game here, and just using the stuff that I've shown you guys. It's crazy. Which button is it? This one. Look at this crap. And like the graphics for the walls and everything, he did that stuff basically all by hand, by just like hand coding put pixel calls. Crazy shit, man. But it's, it's pretty cool. I was impressed. Doing something like this will become a lot easier once I've shown you guys how to load images into memory. And then you won't have to hand code sprites. I do not advocate hand coding sprites for anything, for text or anything. If you guys just be patient, I will definitely show you guys how to load that stuff from a bitmap file, and how to draw text without hard coding it as sprites. We just have to be patient. But yeah, I mean, this guy put in a lot of crazy effort into this. It's the source code for this is on the forums, so if you search for it, you will find it, and you see he's got like he's got like over 1,000 lines of code, just lots of put pixel calls. I don't know, it's crazy, but it's good work. I mean, very impressive. So I'm not asking you guys to do anything crazy like this. This is the thing that I want you guys to do. It's very simple. I mean, I don't want you to. You don't have to do it. I don't really care if you do it or not. But I mean, I think it would be a good exercise for your stuff. Shit, where did I put the thing? There it is. So yeah, make this game or something similar to it. See, notice how I make them, they don't just keep moving in the same direction. If they hit the wall, they bounce off the wall, but they also randomly change their speed and direction without even hitting the wall. So it's just another thing, you can implement. I'm going to post this executable on the, I guess I'll post it with, I'll post it with all the other downloads for the lessons. So there's no extra sprites or anything you need to download for this lesson. It's just, it uses all the same stuff that we used in the original Poo application, with the exception of this thing, which is not a sprite. It's drawn algorithmically, so you don't need to do any huge put pixel call functions or anything like that. But I will put this file, this executable, for download so you can study it if you want, to make sure what the behavior should be. But I mean, if it's a little bit different than this, it doesn't matter, as long as you get the experience of figuring shit out for yourself. And that's it. That's that. That is that. So today I taught you what? Can you remember what I taught you? Because I can't. But give me a second. Okay, I taught you. What did I teach you? I taught you arrays, and I taught you # define for making useful little placeholder variables. They're not variables, they're constants. But yeah, it's good. And I also taught you a little bit about graphics. So yeah, how the graphics works on the system. I also taught you about memory and shit too, didn't I? Because that kind of went with arrays. Memory, arrays, which also links into graphics. It's all just one big incestuous family. So yeah, covered some good ground this time, and we're definitely moving forward. In the future, we still gotta go over structures. Structs. I'm not sure when I'm gonna show that, and we have to do pointers. Pointers are hard and complicated, and I'm not sure how I'm gonna introduce them yet, but I gotta think of something. So yeah, and once we do pointers, then we can do strings, which is text. And when we do strings, we're actually going to be doing those in a console application. So we're going to be putting the framework aside for a couple lessons and just doing console applications to get you guys up to speed with working with strings. And then we have to, once we do strings and that stuff, there's file, input, output, opening files and saving the stuff to files. And there's dynamic memory allocation. This means nothing to you. I'm just mumbling to myself now. But once we do this stuff, then we can do sprites. Because I know you guys are like, I want to do sprites. Let me do sprites. What are you talking about this shit? I want sprites. You will get your sprites. Just hold on to your little tiny penis. Yeah. So for now, we're just going to be moving on. I'm not sure. Next time I'm going to do structures or pointers. I don't know which one I want to do first. I have to think about it. But next lesson, I definitely will be going over the solution to today's homework. So we'll definitely do the solution. And one more thing. You know, we did what? We did the Pooh game. We did tic-tac-toe. So I'm going to have to think of what a semi-trivial game type project to do next for our next kind of capstone project deal thing. And what I want you guys to do is, if you want, I mean, you don't have to, but if you have any ideas of what you would like to do, for what you would like me to do and show you for the next game project thing, you can go on the forum. I'm going to make a topic for ideas for the next game and post your ideas. I don't know. Maybe your ideas will all suck, but maybe there'll be some good ones. Who knows? Just keep it in mind that it can't be like some super complex, like commercial game thing that will take like a whole year to produce, right? It's got to be something simple that I can make in front of the camera in about hopefully in under 3 hours, because I don't want videos that go on for like 10 hours. That's crazy. This video is long enough as it is. So yeah, I want ideas for games, stuff like that, projects to do. Just give me your ideas, what you think would be a nice, simple game that we could use to as an exercise to demonstrate the various programming constructions that we've learned over the course of the lessons. So give me your ideas, what you want to see done. And if I find some good ones there, maybe I'll round them up and I'll put like a poll out, and I'll let everyone have a go at it and see which one is the most popular. And yeah, so if you want to do that, go to the forums and check it out. And now I will leave you to, I don't know, do whatever you're going to do. Masturbate to the Teletubbies. Go for it.